All right, if we take a look at home run hitting problem, hitting a home run. Once again, as we talked about before, they have statistics and calculate statistics for everything now. I mean, and everything is very analytical in regards to um, everything in sports. Everything that we deal with in sports is very analytical. Every time you watch an Indians game, somebody hits a home run, they'll talk about the velocity of the ball as it's going out, as it leaves the bat. What's the velocity of the ball? What is the launch angle of the ball? So they look at all the analytics behind everything, and there's a huge science that's a part of that. I mean, I'd love to be the person that, that's my second job right there. I'd sit there and give all the numbers and do all the statistics and all that stuff. That would be fun. But you got Philadelphia Phillies All-Star Bryce Harper hit a ball with an exit velocity of 115.5 miles per hour. Really fast. Really fast. Most of the time, exit velocities are about anywhere from 90 to 100. If they're hitting home runs, they're usually about 100 to 105 with their exit velocities. He was 150 miles per hour. To left center field at Citizens Park. The fence in left center field is 112.5 meters or 369 feet from home plate, and its height is 4.3 meters, which is 14.25 feet. The launch angle was 75 degrees, 17.5 degrees. Did the ball clear the fence? Did it hit the fence? Did it fall short? We have to do the analytics here. So if we take a look at what is going on. What is going on here? We have Bryce Harper, who is swinging a bat. Looks like a gun. Swinging a bat. The ball hits here and has a launch angle of 17.5 degrees. It has a velocity of 51.63 meters per second. We have a fence that is 4.3 meters tall. And we have a distance from home plate that is 112.5 meters. Now, if the launch angle is not high enough, what will happen is this will fly and donk right into the fence and fall. So the launch angle has to be good enough so it goes over top of the fence. This velocity, the exit velocity, has to be fast enough so it can go over top of the fence. If it's not fast enough, it will just be warning track power. Okay, Miles Straw will be out there in center field just going like this and catching the ball out there in center field. Okay, so there's a lot of dynamics that go here. Is the launch angle enough to get it over top of the fence? And does the velocity carry it over top of the fence if it has the correct launch angle? So if we take a look, we have two, once again, vertical and horizontal that we have to deal with. We have vertical, horizontal, we have acceleration, displacement, time, V initial, and V final. Now, I know when he hits the ball with the bat, he is changing velocity from this direction to that direction, which means we have to have acceleration. I get that, I understand. But we're looking at the point where the ball leaves the bat. From the point where the ball leaves the bat, okay, that's the snapshot that we're looking, the time of frame or frame of time that we're looking at. The snapshot from when the ball leaves the bat to it lands somewhere. Vertically, we still have acceleration of gravity that we have to worry about. So we still have a negative 9.81 meters per second squared. Now, displacement, that's what we're trying to calculate. Do we have enough displacement to get the ball past the fence? Time, we don't know how long it takes to get to the fence. Initial velocity, could we calculate initial velocity now? Yeah. We have our V cosine and our V sine of our launch angle. So we can calculate some initial velocity. So we have 51.63, vertical sine of 17.5, and V initial horizontally, we just deal with the cosine. So we can calculate initial velocity. A lot of times we sometimes struggle with calculating the initial velocity, or we're trying to calculate what velocity do we have to hit at to be able to clear. We can calculate initial velocities here using our components. No, what's our two initial velocities, vertical and horizontal? What's vertical?
15.5 meters per second and 49.2 meters per second.
Okay, we're good with those numbers? Okay, acceleration horizontally. We have no acceleration horizontally. Once again, the ball will hit some air and it will slow it down a little bit. I get that. But for our purposes, we have no horizontal velocity or acceleration. So what we have to determine is when we get to this point, the first thing we have to determine, do we have enough height? Do we have enough height when we get to that point? When we get 112 meters away or 369 feet away, we get 369 feet away. Do we have enough height? That's what we have to determine. Well, the question is, how long does it take to get 369 meters or feet away, or 112.5 meters? So the first question we have to ask is, how long does it take to get to the fence? Horizontally, and that's a horizontal distance. This 369 feet is a horizontal distance. How long does it take to travel the 369 feet, or 112.5 meters? So my displacement is a 112.5 meters, and we're dealing with the horizontal sense. Horizontally, how long does it take to travel to 112 meters, 0.5 meters? So I have acceleration, and I have initial velocity. So we can go back to the v final, displacement is equal to v initial t plus 1/2 at squared. And we can solve for our time. That 49.2. I can't read my own writing. What's your initial velocity horizontally? 49.2. So we can calculate how long does it take to get to that point. Amber, how long does it take? 2.28 seconds. Okay, because this goes to 0, divide 12.5 by 49.2, 2.28 seconds. Vertically, at time equal 2.28 seconds, what's its height? Now, let's talk about, no, we'll just look at the height. Vertically, okay, let's take a look at the displacement. At 2.28 seconds, what is the object's displacement vertically? What is our displacement vertically at 2.28 seconds? And once again, we can go displacement v initial t plus 1/2 at squared. I know my v initial, I know my time, I know my acceleration. We can calculate what is our displacement after 2.28 seconds. What's our displacement come down to, Austin? 9.84 meters. That is our displacement of our object. Now, let's take a look at what is happening here. If I have a baseball bat and I'm swinging a baseball bat and I'm hitting a ball, I am hitting the ball usually from mid-thigh to waist, somewhere in that range. That's where I typically, that's the nitro zone. The nitro zone in regards to if you're swinging and hitting home runs, you're going to be hitting the ball. It's about waist high. Okay, it's not up here. You don't usually hit home runs off high cheese. Okay, because you can't get on top of the ball. It's usually not down here because you're golfing too much. Okay, it's usually somewhere from mid-thigh to waist, and typically the waist-high fastballs are the ones that get smoked pretty good. So if I take a look at a waist-high, what is the height of the object originally? About a meter. It's about a meter. If I look at, I know this is not a meter stick, but here's a yard. A meter takes us up to about right here. So we can approximate the height of the ball being initially 1 meter above the ground when you hit it. So if the displacement is 9.84 meters and I start 1 meter above the ground, that means the height of the ball will be 10.84 meters. Because the ball starts 1 meter above the ground. It starts 1 meter above the ground. So we can add 1 meter to this. So the height of the object when it goes past the fence is 10.84 meters, which would clear the fence by quite a bit. Okay, we have 4.3 meters. We cleared it by 6 meters, which is about 6 meters, about 20 feet above the fence. It went flying. So we have enough height at that point, but what we need to determine then do I have enough distance? We have enough height to get there. If at this point I have a height of this, what's my distance? So if I take a look at my distance, how far we cleared it by, once again, we start 1 meter above the ground. And if we just have a fence there with no stands, when it lands, it's going to land on the ground. So it's going to land 1 meter down. So my displacement in the vertical sense the displacement will be a negative 1 meter. That's if it hits the ground. Now, if it lands up in stands, I get this is an ideal situation. We're playing home run derby out here at Downton Bulldog Stadium out here, the baseball field, where you don't have you have a fence, and when it lands, it's landing on the ground. So vertically, we have 1 meter. How long does it take to vertically go 1 meter, negative 1 meter in displacement is what we're asking. How long does it take to have a displacement of negative 1 meter? Because it's going up, and then it's hitting on the ground. So we are displacing negative 1 meter. How long does it take to displace negative 1 meter? So we have negative 1 is equal to V initial t, which is are 49.2, I'm sorry, 15.5 t plus 1/2 times negative 9.81 t squared. We can add our 1 to the both sides. 0 equals negative 4.905 t squared plus 15.5 t plus our value of 1. And we can run it through our quadratic formula. Once we find the time it takes for it to be a negative 1 displacement, then we can find a horizontal distance with that time, looking at that time. But once again, displacement equals v initial t plus 1/2 at squared. This goes to a value of 0. So our displacement is equal to v initial, 49.2, times this time. All right, go ahead and finish that up. Have a good weekend. Enjoy your day off tomorrow.